Okay, guys, don't leave. We have another presentation. My name is Ali Omar. Welcome to this presentation of NASA's air quality from satellites. Today, I'm going to present some of the modeling and some of the measurements that NASA does from space that can be used for air quality. In this image, this is an image of a simulation from the guarded GMA Air Office that shows the different aerosol types as they are emitted at the surface, and they are transported and they go through chemical transformations. And you can see the green part is organic organic carbon and elemental carbon that comes out of biomass burning in forests in Brazil, parts of West Africa, and Southeast Asian forests. The blue is sea salt, which you can see is mostly in the oceans. These are produced by winds that blow over the ocean and cause the ejection of aerosol particles into the marine atmosphere. The whitish aerosol is sulfate aerosol. Sulfate aerosol is mostly produced from the combustion of fossil fuels. Most types of fossil fuels contain some kind of sulfur. And so when that's combusted, it produces sulfur dioxide. That sulfur dioxide is oxidized in the atmosphere. And you can see that in most of the industrial regions, you have sulfate emissions. Those are the white streaks that you see in those anticyclonic motions. You can also see some white streaks in the oceans because in the ocean, too, we have dimethyl sulfide that can be oxidized to sulfate particles. And so you see some of them that follow the wind patterns in the Southern Ocean. The last aerosol type here is dust. As you can see, dust is in a brownish color. It's wind-blown from the surface of the desert, and it's mostly in West Africa, the Arabian deserts, and some of the emissions from Asian deserts. And so this picture gives us an idea of what kinds of measurements we can expect from space, what kinds of aerosols are present in what region, and how they are transported. And occasionally you see eruptions of sulfate, which is the white parts that come from volcanic eruptions. And so as we go through a time series of this simulation, you see that there is some eruption from volcanic eruptions in those islands. Eric, can we move on to the next one? So one of the important gases that we observe from space is nitrogen dioxide. Nitrogen dioxide is formed whenever there is combustion in the ambient air. We know our air contains 78% nitrogen and 20% oxygen. And so whenever there's a combustion process, we have the production of nitrogen dioxide. Nitrogen dioxide is a noxious gas. It's one of those pollutants that the EPA controls that are not good for health. And so monitoring it both by ground monitors and from satellites is important. In this case, we see that there are hotspots of nitrogen dioxide. Those are the column concentrations of nitrogen dioxide. The red towards the white are high concentrations, and the dark colors are low concentrations. We see that during the biomass burning seasons, both in the Brazilian forest and in Africa, that there are elevated concentrations of sulfur dioxide. We see that there is a lot of sulfur dioxide emission. Sulfur dioxide is also emitted by the combustion of fossil fuels. And so in industrial areas of the United States and also in Europe, you see that there's a lot of production of nitrogen dioxide. And then, of course, in Asia, China and Japan, those industrialized regions, there is also a lot of production of nitrogen dioxide. And then you can see some cases where you see point sources of sulfur dioxide. These sources where you have either large power plants or smelting operations that produce a lot of sulfur dioxide. And so while a lot of this is forest fire burning, some of these are actually industrial processes. And then you can pinpoint some of the cities where there are hotspots of NO2 production. This measurement is from the OMI instrument. This is the ozone measuring instrument that flies aboard NASA's Aura spacecraft and has been providing these measurements for a long time. In subsequent visualizations, we'll see how the concentrations of this gas has been changing over the years. Can you go on to the next one? Okay, so this is a snapshot of nitrogen dioxide in the United States, and we can see how it has changed between 2005 to 2007 and 2009 to 2011. These are 2-year averages of that period compared to 2-year averages of the next period. So in these 5 years, you can see how nitrogen dioxide has reduced in several of these cities. This is really a good news story because it tells us that nitrogen dioxide is decreasing and the air is getting cleaner, and most of the result of this is the regulations that have been imposed on a lot of the emitters of nitrogen dioxide to reduce their emissions. And so we see that in every city that NO2 has been decreasing quite dramatically, between 30 and 40% over this period. If you look at a city like Denver, the hotspot is almost gone over these years. And as I said, this is a combination of the regulations and also improvements in technology that reduce the amount of NO2 that's emitted into the atmosphere. Can we go to the next one? Okay, this is an image where we have transposed 2 different measurements. One measurement is the vegetation index. How green is the planet? And the other image is the amount of carbon dioxide at any given time. And so if you focus into one of the regions, say the northern hemisphere, around the May time frame, the carbon dioxide maximum is seen at that time. That corresponds to the minimum in the vegetation. That's really telling us something that we know, that carbon dioxide is taken up by vegetation, and so as vegetation goes up, the carbon dioxide concentration decreases. And so the transposition between the images from MODIS vegetation index and AIR's carbon dioxide, these 2 instruments are both on the same satellite, so we can make these measurements simultaneously. And so we see the interplay between the increase in the NDVI, or the vegetation index, and the decrease in the column carbon dioxide concentration from the AIR's measurement. And it gives you an image as if the Earth is actually breathing, taking up the CO2, and then releasing it when the vegetation goes away. Next. Okay. Okay, this is an image showing how we can use measurements from 2 different satellites to pinpoint the location of an air and a pollution source in a region. It's not. Yeah. So in Singapore, in Singapore in September, there was a big smoke incident where there was a lot of smoke. We're comparing this period. In this period, there was in May. This is May 20. Yeah. So during May 29th, it was very clean. And when you look at September 25th, there was a large incident of smoke pollution that was advected over Singapore. And you can see from the first image, which is the MODIS image, that the smoke covers that whole region. This smoke came from the Indonesian fires that happened at that time. As you can see, there is smoke everywhere. We have another instrument called Calypso. Calypso is the lower measurement that shows the location of these layers. Because Calypso is a laser-based instrument, it can tell you exactly where the layers are in the column. And so you can see the layers of the smoke aerosol during that period. During May 29th, it was relatively clean and there was no smoke layers. And then when you see the image during the smoke period, you can see that there are a lot of smoke layers at about 5 or 6 kilometers above the surface of Singapore. And so this image for the Calypso track that went across the city of Singapore, shown by that line, shows that there's a lot of smoke in that time. And when you compare it to the time when there was no smoke, there were hardly any layers. And the only layers you see here are layers of the smoke that is distributed in different parts of that map. And so this is how we can use two measurements. One measurement measuring the vertical column and the other measurement measuring the horizontal column to tell us the extent of pollution in a particular region. In this case, Calypso is a laser-based instrument that orbits the Earth and repeats in the same place about every 16 days. And so when you get the track that corresponds with that pollution incident, you can go in and look at exactly where the smoke layers are. This was a pretty serious smoke incident. They had to give people masks to go out. It was the level of smoke was about 10 times what they experienced in that region for that period of time. And so the two measurements gave us an indication of not only where the smoke was, what the extent of the smoke was for that case. I think this is my last one, right? Yeah. So if there are any questions, I'll take them.